use the tools I give you to verify things that are on the graph. It's the same thing when you get to calculus. If I give you a function, graph it. If you go to University of Maryland and take Calc 1, Calc 2, Calc 3, they won't let you use a calculator, but you're still going to use it when you're practicing, because the whole idea of what we're trying to do here is get you the understanding of the graphs without having the graph in front of you, right? When does it turn? When does it hit the height? When is it increasing? Um, you know, all of these little subtleties. So if you practice with the calculator and verify things with the algebra and calculus, then you're going to understand it quite well. Okay. So we're looking at a rational function. The book uses R of x a lot for rational. I like P of x and Q of x. And so obviously we're looking at polynomials in the numerator and polynomials in the denominator, right? So where P and Q are polys, and Q of x does not equal 0. I can't divide by 0 even if it's a function, right? So there's lots of things we're going to be looking at this. I want to think of three versions of this particular function. I want to think of one in standard form, one in factored form, and one in reduced form. So we're going to be looking at standard form, factored form, and reduced form. In standard form, I have to be careful about multiple terms, right? I want to wrap multi-terms. Not like a M&M type of way, but just with parentheses. Wrap the multi-term numerator divided by wrapped multi-term denominator. And reduced form is a little bit strange, and you'll see it happen a couple of times. But sometimes I'll have a matching factor in my factored form in numerator and denominator, and they cancel. But I have to make sure I remember to adopt the domain of the original in the reduced form. Adopt the domain of the original form. Adopt, I don't know if adopt is the right word, but make sure it carries through. Whatever your domain is of the original, even if you reduce it, you have to keep that domain. Okay. We're going to look at points on here, of course, intercepts, x and y if they exist, right? We'd want to look at asymptotes. So we could have horizontal, vertical, and obliques. Horizontal asymptotes, right? Vertical asymptotes, and obliques would be some kind of diagonal asymptote. I usually skip that, but I forgot to skip it. And that's all over the homework, so I'm just going to teach it to you instead of skip it. It's not a big deal in Calc 1. And how we get the obliques is we long divide or synthetic divide, which is what we just did, right? Anyway. What else do we need? Domain and range. Range right now from us is just looking at the graph and getting a range. In chapter 5, we're going to learn how to get the range from the function itself, meaning not having to look at a picture. But it's not easy, so we got to wait a little bit. We're going to look at long run behavior and short run behavior. The short run behavior The long run behavior is easy, and I'll show you how to do that quickly. The short run behavior is weird, and I use a technique. I can't remember if my father came up with it or I came up with it, but we want to look at two mother functions. So 1 over x and y equals 1 over x squared. So the short run behavior is going to be related to that. Now, of course, we want to graph it. That's probably the first thing on my list, but I put it last. And I think I have everything. So this is everything we're doing in 4.4 and 4.5. 4.4 is just going to start asking for domain and then some asymptotes, and then 4.5 is going to ask for everything. But I'm just going to do everything the whole time. I don't expect you would be able to finish this homework in one night. I would expect this might take a week because it's complicated, it's new, it's weird. But again, use the graph to verify. I think I have everything. So, but if I forget something, I'm going to come back to this list and add something to it. All right, let's look at a problem. So we'll look at homework 17, number 1. Let me open it. Give me 1 second. Almost there. So here it is, homework 17, number 1. And it starts real simple, which we like, right? It's just one problem, 8x over x plus 2. And they just want me to find the domain of this, right? So f of x equals 8x over x plus 2. And so what's my rule for domain right now? I only have 2. I cannot divide by 0, and I cannot take an even root of a negative, right? We're gonna add more domain rules when we get to log functions, and we're gonna add another domain rule when we get to trigs, right? So, but it's really that simple. You always will have these simple domain rules. So in this one, the only thing I can't let x be, right, is I can use any of the real numbers except for -2, right? So in interval notation, which is the book would rather want -8, negative infinity to -2, union -2 to infinity, right? There's my domain. So everything but that singleton x equals -2. Does everyone agree with that? So, of course, I want to graph this right away, right? And so this is what 8x divided by x plus 2. I'm just wrapping that second term when I'm going into my TI. When I go into Desmos, it's a little bit easier. But I want to look at the asymptotes here. So first of all, my vertical asymptotes come from, it's such a weird word. I always laughed at it when I heard it as a student, and I always wondered why no one was making a joke about it. So vertical asymptotes, when the denominator is 0 and the numerator is not 0, okay? When r of x equals a number over 0, x is a VA, a vertical asymptote. So we know that x equals -2 is a vertical asymptote. What does that mean? That means there's no value on the graph at -2. So the graph will never hit that or never cross that vertical line. I want to look at the horizontal asymptote or the long run behavior. So we kind of remember that long run behavior as us becoming our parents, right? So I want to look at f of x equal to 8x over x plus 2 as x goes to infinity. So what happens is the numerator adopts the mother and the denominator adopts the mother. So 8x over x plus 2 is really similar in the long run of 8x over x, which is 8. So that's my vertical asymptote. So y equals 8 is the vertical asymptote. So 2, 4, 6, 8. Now, a function can cross a vertical, a horizontal, oh, I said vertical, a horizontal, right? A function can cross a horizontal asymptote in the short run. So early it can cross, but in the long run it never crosses, okay? So now here comes short run behavior. How are we doing here? Am I going too fast?
A little bit.
Okay, slow me down, please. Don't let me. You're paying me, right? I'm your Uber driver. So I like to think, let me go back to horizontal asymptotes. I like to think of Dave Chappelle imitating Rick James, right? Dave Chappelle imitating Rick James. Just keep your, yeah, you ever see Chappelle show? So if I have $1 million, right? I've got $1 million. In fact, make it $1 billion. No, a trillion. No, sorry, a godzillion dollars, right? So downstairs I have a godzillion dollars. Do I care about $2? If I have that much money, do I care about $2 anymore? Hell no. I'm not even gonna. I'm not even gonna bend down to pick up $2 if I see it on the ground, right? And so that's what I'm saying. I'm saying I'm rich, bitch. So I'm saying I don't need. I don't care about the other terms. I've got so much money just from the leading term that the other terms are insignificant. So that's why this thing's really behaving like 8x over x or 8, right? I've got so much money that only the leading terms are really what I care about. So, so again, but thinking about the mother, right? The mother of the numerator, mother of the denominator, and then what happens at the end. Now, what happens at the end if I have the same uh, kind of x term, x to the first over x to the first, I'm always going to get the leading coefficient. If I have an x squared over an x, I'm going to get an oblique, right? Or an x cubed over an x, I'm going to get an oblique. When the numerator is at a higher power, I'm going to get a strange curve in my asymptote. And when the denominator is bigger, I'm going to get just a zero, right? I'm going to just get a zero. And hopefully I'll get to one of those. So short run behavior is my own process. So I doubt you've seen it before, but what I want to do is I want to look at what happens when I plug in a zero denominator. So uh, x equals -2 is not in the domain, right? So we look at f of -2, and we get 8 times -2 over x plus 2. I can't plug in the -2 downstairs because I get a 0. So I plug in that piece out of the domain everywhere except for where I can't. So I get a -16 over x plus 2. And then I'm thinking of the mother function there, it's like a negative 1 over x, right? Yes, it's a negative 16 over x, but who cares about the 16? It's just going to stretch it out. So I want to think of that mother function, right? Like here, there's the negative 1 over x. But that's going to be present at the vertical asymptote. So looking back at my picture, I should see that negative 1 over x shape over here. So you see that same shape of negative 1 over x in between my grid there. It's almost like I've moved my origin. Remember when I was moving that box, that 1 by 1 box? It's again, I'm moving my origin to where this vertical and horizontal asymptote meet. And I guess the other thing I should get are intercepts here, but that's kind of obvious. I've got an intercept of 0, 0. Right? When I plug in 0 to x, I get 0. Right? And there's the idea. That's our first one. It's not that easy. It's quite complicated. It's a lot to remember, but if you're going to have a formula sheet, you've got to have some step by step. You got to give me some explanation on the paper, right? You got to let me know what's going on the paper. How are we doing here? Short run behavior is a little weird, so you got to let me do a couple more before you say I get it or I don't get it. You probably right now you're saying, what the hell is going on? All right, let me do another. Everyone okay? So this is number 3, homework 4.2, no, 4.4, right? Homework 17, number 3. So homework 17, number 3. And I have the function 5x over x minus 4, 2x squared minus 5x minus 3 is the downstairs. This is neither factored nor standard form. So I want both. So I'll get the standard form pretty quick, right? What do I get? 5x squared minus 20x all over 2x squared minus 5x minus 3. There's my standard form. If I'm going to my calculator, I'm going y1 equals parenthesis, right? Numerator divided by parentheses denominator. If you don't do that, you're going to have some strange results. I want them both factored, right? So I want them both factored. I want to get that factored form and see if I can reduce anything. So upstairs is already factored. Thank you. Downstairs I can factor using a split the middle term, right? So I want to factor on the side here 2x squared minus 5x minus 3. And of course I know 2 times negative 3 is negative 6. Cindy, please, and anyone, if I'm going too fast because I feel like I am, slow me down. Right, I have a cop follow me home for like 10 miles, and I get home and he comes up to my door and he gives me 50 speeding tickets. I'm like, that's not fair. Stop me when you see me speeding. Give me 1 ticket, right? And then let me go. Don't just keep following me, keep shooting me with the radar gun and just keep writing tickets. So I'm going to split the middle term here. I know I can have factors of 6 that add to 5 of 1 and 6, right? And so one of them would have to be positive and one would have to be negative. And it looks like, oops, and it looks like it's my negative 6 and positive 1. So I split the middle term. And please show me your factoring. Don't just give me something factored on the page. When you get to calculus, you don't have to show me your factoring. But so what do I get? 2x squared minus 5x minus 3. I'm going to split the middle term with a minus 6x plus 1x. And I'm going to factor by grouping, taking out a 2x and taking out a positive 1. So I see x minus 3 and 2x plus 1. And there's my factored form. How are we there? Nice. Elmer, Elise, Ryan, Jamal, thank you. Everyone else okay? I do have the chat open if you want to chat. Thuria and Wilder. I found the only thing I like about teaching remote is that when a student is having trouble, they can chat to me privately and say, I don't get it, or what the hell you doing, or I think I'm going to try and bring that into the face-to-face classroom. And so you'd be able to text me on my phone while we're working, while we're in class, and tell me. So, right, I did all of this work on the side here. I always like to put like side work. And if I'm not sure about it, I cross it out so it can't be graded. But since I know it's right, I can cross it out anyway, and then at least it explains where my factoring came from. So now, here's my function in factored form, right? 5x times x minus 4 times x minus 3 times quantity 2x plus 1. So this happens to be my reduced form. It doesn't reduce, nothing cancels. If something canceled, I'd have a third new form, right? But I want to make sure I adopt my domain here. So what's my domain? It's all of the reals, right? Except for minus 1/2 and 3. Right? Do you agree with that? X equals 3 gives me a 0 downstairs, and x equals minus 1/2 gives me a 0 downstairs. So minus infinity to minus 1/2. Union minus 1/2 to 3. Union 3 to infinity. So I'm taking out those pieces. And I'm actually I'm creating a number line with 2 holes in it, right? At minus 1/2 and 3. Let's find some intercepts, right? Well, when the numerator is 0, I get x intercepts, right? So 0, 0 and 4, 0 are my intercepts. And of course, the y-intercept is 0, 0, right? When the x is 0, I get a y-intercept. When the y is 0, I get an x-intercept. So the x-intercepts come from when x is 0, when the numerator is 0. What about my VAs, my vertical asymptotes? Well, that's x equals 3 and x equals minus 1/2. That's easy whenever the numerator is 0, but the denominator is 0, but the numerator is not. Horizontal asymptote, long run. I want to look at my standard form here, right? What do I get? 5x squared minus 20x over 2x squared minus 5x minus 3. So that really behaves like 5x squared over 2x squared, sorry, which is 5 over 2. So y equals 5 over 2 is my HA. I'm not going to look at short run behavior yet until I get my graph going. So let me look at the graph, okay? So I want to go to Desmos. Are we okay to go to Desmos? And you may need a minute. Yes, Doria, what's up?
Do we need to show work for the intercept?
No, not really. I know you know how to plug in zeros. So, I mean, Doria, always err on the side of show more work than not show work, and then you'd be safe. All right, so let me put the original function in standard form, right? And I forget it already. Someone had the standard form for me here. Is it 5x squared?
Yeah, it was 5x squared.
Yeah, minus 20x?
Yeah, minus 20x.
Okay, all over, and if you see, I don't have to do the parenthesis on Desmos, all over.
2x squared minus 5x minus 3.
Thank you. So there's my function. I got a couple of intercepts. I got 0, 0. And I got 4, 0. So they're all my intercepts. I got a horizontal asymptote of y equals 5 halves, right? And remember what I said. In the short run, a horizontal asymptote can be crossed, but not in the long run, not all the way at the ends. It never crosses the graph. That green graph will never cross that x horizontal line, that red horizontal line, as x goes to infinity. It can cross it in the short run, but eventually it doesn't. It never crosses. I got two vertical asymptotes of x equals negative 1/2 and x equals, I forget, 4? What was it? X equals 4? X equals 3, right? Yeah. So there are my vertical asymptotes. A graph will never cross a vertical asymptote. It's because it's where the graph doesn't exist, right? You can't plug in that value to the function. You can't get a height at that function. Now, I want to try and look at the short run behavior at 3. So looking at my mouse here, you can see a bend this way and a bend this way. And I'm saying that looks like the opposite of 1 over x. Okay? Right? I'm saying, I'm saying that y equals 1 over x has this shape, and y equals negative 1 over x has this shape. Right? Right, I'm just switching my positives and negatives, right? So I want to look at what happens at f of 3. So first of all, f of x is 5x times what? I forget, x minus 4? No, x minus 5? 4. And then downstairs I got what, a 2x plus 1 and an x minus 3, right? So I want to look at f of 3, and this is my short run behavior, right? So I'm taking all of the places that are not in the domain and plugging them into the function when I can, meaning when I don't get a 0 downstairs. So I get 5 times 3 times 3 minus 4 over 2 times 3 plus 1 over an x minus 3. I can't plug it in there, right? This piece can't be touched with a 3, right? So what do I get? I get a 15 times a negative 1 over 7 times x minus 3. Okay, I have negative 15/7 times a 1 over x minus 3. So you can see my mother function of 1 over x, but the coefficient is negative. So the mother is really, right, the mother of this one is really like a negative 1 over x. And so I should see that shape at x equals 3. I should see that shape at x equals 3, right? So at x equals 3, 1, 2, 3, at 3 halves, right? Right around there, I should see the upward piece and the downward piece. And look at my curve. Look at my curve on Desmos. I can see the upward piece here, right? That upward curvature and the downward curvature over here. So it looks like negative 1 over x. I guess I could put that piece in. I've never done this before. Negative, what was it, 15 over 7? Was it negative 15 over 7?
Yeah.
Negative 15 divided by 7 times 1 over x minus 3. And you should see, you can see kind of that curvature of the purple curve represented in the green curve. It's not perfect, right? But you still see the green curve matching with the purple curve. All right, let's do another one. How are we doing? What did I lose? A student? 4, 8, 12, 16, 19. I lost a student. Let me redo attendance. All right, let's do another one here. So here we go. This is number 4, and believe it or not, I'm doing everything from 2 sections here, right? All they're asking me here is what's the domain, and then I'm doing everything. I'm saying let's find the intercepts, let's find the horizontal asymptotes, the vertical asymptotes, let's find the short run behavior, the long run behavior, let's find whatever, right? I'm just trying to do everything at once. So on this one, we're going to have a reduced equation. So this one is pretty nice already for the standard form. So I've got f of x equals, and my numerator, oh boy, I can't see it, x squared minus 6x minus 7, I think. I took a picture, but it's blurry, over 5 times x squared minus 49. Just let me double check it. Yeah. So I'd rather go to standard here, just because I've seen so many mistakes made by having factors instead of having just standard form. But I mean, if you can do it right, I don't care. 5 times 49.
245.
245, thank you. So again, when I put these into the y1 in my calculator, I want that numerator wrapped and denominator wrapped. You know, not in like a M&M style, in a parenthesis style. I can factor that numerator pretty easily, right? What do I get? I get negative 7 and 1. Right, everybody with me there? And the denominator easily too. X minus 7, x plus 7. Right, is this okay? Let me know. Don't let me go too fast. Yeah, Jamal, you there? You okay?
No, I was going to ask how you got the factor, but I would just do it like on the side work.
Yeah,
I mean,
yeah.
for the numerator.
Exactly. Yeah, so this one I'm going factors of -7 that add to -6, right? This one factors of 49 that add to 0.
Got it.
Yep. Now notice this is my factored form, and from here I get my domain, right? My domain here is what? All reals minus plus or minus 7, right? But if I can see that I have a repeated factor that cancels, I still want to adopt my domain for my reduced version of this, which is 4 times x plus 1 over 5 times x plus 7. I have to consider the domain of the original function. Even if I reduce, I have to keep that domain of the original function. So what happens is, at x equals -7, we have a vertical asymptote. At x equals 7, we have a hole, okay? And this is also called a removable discontinuity. I call it a manhole cover. I can take that point, I can take that lid off of that one point, and then someone could fall in, or I could fill it up, right? So that it's safe to walk on. And this is a calculus topic. It's called a removable discontinuity. And you can't see it on the calculator, which is what is pretty interesting. You can see it in the table, but you can't see it on the graph. How are we doing here? So the important point here is that if I have a denominator of 0 and the numerator is not 0, it is a vertical asymptote. If the denominator is 0 and the numerator is 0, it's called a removable discontinuity, and what happens in the graph is there's just a hole in the curve there. What do we have for our horizontal asymptote, long run behavior? Y equals what? Anybody see it real quick? Anybody?
4/5.
4/5, nice. When the mother functions of the numerator and denominator are the same, I just need the ratio of the coefficients, right? I don't care about short-run behavior. You've seen it twice already, so let's just go right away to Desmos and graph this. Or maybe the calculator. Let's do it on the calculator, just so you can practice. You can do this along with me on the calculator, and we can look at the table there. So I'm going to open up my calculator and go to y equal, and I'm going to put in that standard form of this thing, and I'm going to forget, but you'll remind me, I think, right? Ah. 4x squared, is that right? 4x squared, somebody remind me, 4x squared is right? Minus 24x, oops. Minus 42, no, 28, help me please, am I right? Divided by,
Yeah, it was 28.
Yep, divided by parenthesis 5x squared minus 2 what? Minus something, help me. Fine, I'll just do everything myself. Minus 245. Don't help me then. And graph standard should give me a pretty good picture. So you see at -7, you can see my vertical asymptote, but at 7, there's no vertical asymptote, but there's a hole there, right? And if I look at that graph, second table, you can see when I go to 7, I see an error. right? Because it can't calculate it. It can't calculate that particular value at that point. Of course, we know how to find the value, right? We know how to find the value. It's short run behavior, right? So,
Professor, which one's the whole again?
yeah, at 7. So
Okay.
I get 4/5 times 7 plus 1 over 7 plus 7. So I get 4/5 times 8 over 14. So I get 2 times 8 over 5 times 7. It's happening at a height of 16/35. So at the height of 16/35, when x is 7, there's a hole in the graph, right? There's a hole in the graph. I can find the height of the hole by doing short run behavior. Plug in that value that I'm not allowed to plug in everywhere except for when I'm not allowed to plug it in, right? What do you think? Not too bad, right? I mean, it's a lot. Honestly, it's a lot. It's just dense, right? A lot of writing, a lot of vocabulary, a lot of things to try and think about and graph, right? And then you want to add, right? You want to add some language to the page, some writing to the page, so I know how, what you're doing, what you're communicating to me when you turn in the test, right? I think that's it for 4/4. Oh, maybe I should do an oblique real quick. Let me find an oblique in 4/4. Here's an oblique. So do you see why this is an oblique? I've got an x cubed as a mother upstairs, and I got an x squared as the mother downstairs. And so when I divide these, I'm going to get a linear, right? X cubed divided by x squared is an x. So my oblique is going to be a straight line. When I have an x, let's say an x to the 5th over x cubed, I'm going to get an oblique that's a quadratic. And you'll see what I mean when I do a problem. So let me do this one. So this is almost our last thing to talk about, obliques. But then we'll take a quick look at some of the 4.5 homework. So this is homework 17, number 7. And we're talking about an oblique asymptote. So I've got the function y equals x cubed minus 27 over x squared minus 4x plus 3. And so that's already standard form. That's nice. I know the downstairs factors pretty quickly into what minus 3 minus 4, right? I do those pretty quick because I've been teaching this for 25 years, but does everyone agree with that?
I agree.
Yeah, the factors of positive 3 that add to negative 4, right? Worst case scenario, you're doing the tree, right? 3, I'm sorry, yeah, 3 is 1 and 3 or 3 and 1, and they're both positive or both negative, right? And there it is. Now the upstairs factors into x minus 3 times something, and I'm going to get that result with synthetic division because I'm too lazy to memorize it. It's pretty clear that 3 times 3 times 3 is 27, right? Or I could graph it, x cubed minus 27. I can graph that and see it goes through 3. But then I want to use my synthetic to finish it out. 1x cubed, 0x squared, 0x minus 27. Everybody with me here? I'm using synthetic to show that 3 is a 0. Nice. I'm going to bring down the 1 and I'm going to multiply and I'm going to add. Multiply and add, multiply and add. Got it. So this piece right here is that rest of that quotient x squared plus 3x plus 9. And there's my factored form. So I've got my standard, I've got my factored, and now my reduced, right? Y equals x squared plus 3x plus 9 over x minus 1, right? Because you see the matching factors cancel with each other. But I still need a domain of the reals minus 1 and 3, right? I can't let 1 or 3 into my domain. So now I can use my original standard, or I can use my reduced to find the oblique asymptote, right? And let's do long division, right? So let's do x minus 1 into x squared plus 3x plus 9. Everybody with me? Anybody need a moment? So I'm asking x times what is x squared? And the answer is x. And I'm lining up all my x terms with each other. And then I come back and multiply to everything. I get x squared minus x, and I change my signs and add. First term goes away every time. I get 4x plus 9, and I rinse and repeat. But don't let me go too fast. Everybody okay? Now I'm asking x times what is 4x, and the answer is 4. And I come back and multiply, I get 4x minus 4, change my signs and add, I get a remainder of 13. I don't care about the remainder of 13, but my oblique asymptote is y equals x plus 4.
Professor, how come we don't care about the remainder?
Because this guy is really y equals x plus 4 plus 13 over x minus 1. And when x goes to infinity here, 13 divided by infinity, 13 divided by quadruple infinity is 0. That remainder gets minimized as x gets bigger and bigger and bigger. And it really behaves just like the mother in the long run. It just really behaves like x in the long run. So, of course, the 4 doesn't count, the remainder doesn't count. So, but in the short run, the x plus 4 will look better. So that's what we're going to do. We're going to take a look at this on Desmos. Upstairs, I had x cubed minus 27. And if I grab all of that and hit divide, and then downstairs, I forget what I had already.
X squared.
Thank you.
Minus 4x plus 3.
Nice, thank you. Oh, you gave me the factor. Can you give me the standard?
The standard was x minus 3 and x minus 1.
Oh, yeah. No, yeah, I wanted the first one you sent me. You were right. X squared minus 2 plus 3, right? Minus 2x.
Minus 4x.
Okay, thank you. Sorry. 4x plus 3. I could do it. And so there is the function, and you can see this kind of diagonal happening, right? Which is my oblique y equals x plus, I forget what I had. What is it? X plus 1? No, x plus what?
4?
Yeah, x plus 4. Thank you. There it is. So you can see that black curve is getting closer and closer to that red slant line as I go to infinity and minus infinity. We had a vertical asymptote at what, 1? Y equals 1 was a vertical asymptote. I'm sorry, x equals 1 is a vertical asymptote.
Y equals 3.
And yeah, and we had a hole at what was it at? Where was our hole at?
X equals 3.
Yeah, x equals 3. Right, so we want to find the height of the hole in the reduced equation or the original equation. I'll use the reduced. 3 squared plus 3 times 3 plus 9 over 3 minus 1. So 9, 18, 27 over 2. So at a height of 3, x is 3 and a height of 27 over 2, 3 comma 27 divided by 2, there's a hole in the function there. I can see that it hits, right? I can't tell that there's a hole there because it's infinitely small, right? But there is one there. Pretty cool. It's a lot of work. It's dense, right? There's lots to write, lots to think about, lots of practice to do here. Let's take a look at that next homework assignment. So just want to look at homework 18 real quick and make sure there's no surprises in there. So it says analyze the graph. It means do everything I just taught you how to do. And it's not going to be any different for any of these problems. And it's going to prompt you for everything, right? So like if I show the answer here, it's going to prompt you for a bunch of things. Oblique asymptote, horizontal asymptote, what points, what's your domain, which is the graph, etc., etc. So you're set. I taught you how to do everything on these two homeworks. And it's a lot of work, so even though I taught it in an hour and 10 minutes, doesn't mean it's going to take you an hour and 10 minutes to do it. It's going to take you probably 5 hours to do it. But you got to chip away, right? Don't be afraid of the work. Don't be afraid of getting something wrong. Ask me for help. That's what my job is, right? Cool. Let me stop my recording.